Okay. Today, the unit we are beginning today is a mini unit. So this won't last very long. A few weeks and we'll take a test. This test will only count for 20% of your overall term gain versus the 80% that occurred in this last. So this will be our next term. Then we will have another test in term 2 towards the end that will count for 60%. So similar to this term, but just slightly different. Okay. Don't take any notes for a minute. Like, there really are no notes to take. It's just, if you will understand this big idea that I'm about to present to you, you're all set for this unit. This unit's a lot simpler. There's just kind of one big idea and then a bunch of rules, the green sheet, that you've got to understand how to use. But it is critical that you understand the big idea. So here's the big idea. So talk to me until it feels good to you. This is not new. You've seen an equation like this before. G of x equals 5x squared. Raise your hand. Collect some extra credit. Get back on the path to an A. What is the purpose of that formula? I ask this question all the time. What's the fundamental purpose of that formula? What is its most basic reason for existing? Let's go, Luke.
So you can plug in x values and get y values out of it.
So I take this formula, plug in x, I find y, I create a list. Don't forget that you will be asked to do the opposite. There will be cases where they'll give you the y and you have to find the x. Okay, how many knew that? 1, 2 for Luke. In Unit 1, we learned the word derivative. Okay? You have to remember that derivative has several meanings. The derivative of this function also means the tangent slope of this function. So just say it out loud. Here's a graph of that function. How many points are displayed on this graph? Say it. There's an infinite number of points displayed. Similarly, there are an infinite number of tangent slopes. So the derivative of this function isn't one thing, like one number. It's a whole bunch of numbers. But each of those values represents a tangent slope. Okay? Tangent slope means rate of change. When we're talking about derivative, we're talking about the tangent slope at a point, or the rate of change at a point, or the instantaneous rate of change, or the slope at a point. Okay, all of those different words you have to be comfortable with, because as you read test questions, they will use all of those different words. Anyone need me to go through that list again, just what does that mean? Okay. So we have our graph. It's a whole bunch of different xy coordinates. We have our formula here for finding all those xy coordinates. In the last unit, we talked about how to use your calculator to find the slope at a point, to find the derivative. Well, here's what the calculator actually does to compute that slope. Or it does something close enough that this is a relevant example. So the calculator creates a secant slope to the right of the point. So that's what I've done here. There's this slope here in green that is to the right of that point A. And if I move point A, the computer just kind of tracks that and keeps that slope. So we're going to go to 1,5 as an example. If I can get it to stop on 5. Ah! This is going to be painful. Come on. Success. Okay. So the computer will find a slope to the right. Calculator does something similar. Slope to the left. The values of those slopes are listed here. 15 versus 1. So very different slopes. But as you move the secant, make the secant shorter and shorter, you should notice something about the two different slopes. It's not really complicated, it's kind of common sense. As I make these secants shorter and shorter, the two slope values become closer and closer to being the same. If I make them very short, these two secant values again get closer and closer to being identical. Okay? In reality, it does not matter how short I make them. They will never be the same. But they become infinitesimally close to being the same. As close as I can get them on the computer is about here, or the computer will crash. So I can get to there. They're still not identical, but they're very close. I was able to mess around for about an hour and get the computer to do this. That was an hour's wasted time. That's how close I could get them. I was very determined to get them close. Wouldn't get any closer. If you could keep pushing them in, this number would become something like 10.0000000001. And this number would become 9.999999999. So Isaac Newton's conclusion was, even though I cannot calculate the slope at a point, because it's not possible, if I find the two secant slopes and just make them really, really short, I have accomplished the same thing. I've figured out what the slope at the point has to be. So the way you calculate the slope at a point is really by doing two secant slopes. Question? Okay. They don't test you heavily on how to mathematically do that. The concept is important. That's going to help us throughout the rest of the year. Remembering that when we find the slope at this point, all we're really doing is doing a secant to the right, secant to the left. That's all we're doing. Making the secants really short. Okay? We just don't spend the time in class to do the mathematical computations to accomplish that. In a college level calculus class, they typically have you do a little of that. For some classes, quite a bit, but AP does not, so we won't do it here. Questions? Please.
So the tangent slope of the one that we just looked at would be 10 because they're both close to 10.
Perfect. It's perfect. You can see that because the two secants are surrounding a value of 10, the conclusion is that it doesn't matter how short we make them, they just seem to get closer and closer to surrounding 10. And so the conclusion is, oh, the value must be 10. It's the idea of a limit. That in the limiting sense, hey, that slope at that point must be 10. Perfect. Super. Good. Please.
If we don't have two small secants, but we have one large and one small, like in this example, would you just do the right secant subtracted by the left secant?
2 points, no. The only way to calculate the tangent slope in the middle, to actually calculate it, is to literally make this infinitesimally short, make this secant infinitesimally short, look at the two values and come to a conclusion that, oh, it's clear.
So is there some way to do that on the calculator?
The calculator just does it automatically, like without you doing anything other than just pressing the right buttons, like we did a while back on the homework. We used this symbol on our calculator, and it just does it for you. This unit is all about learning how to use the shortcuts on the green card to do it by hand. So the green card contains a bunch of shortcut rules that people have figured out that, hey, rather than create these secant problems, finding two slopes and then making them short, these shortcuts accomplish the exact same thing. They're just the result of doing that type of analysis, and then we use the shortcuts because it's a lot quicker. So, 2 for Luke. Other question? Okay, it's crucial that you understand rate, because tangent slope means rate. So look here. Secant slope also means rate. The difference is tangent is instantaneous rate, secant is average rate. So as an example, if I put this point right there, come on, stop. It's telling you that the rate of change from A to C is 15. It's really 15 over 1. That tells you that if you want to get from this point to this point, you have to make a change in x of 1 and a change in y of 15. That's what rate means. Question. So earn a couple of extra credit points and tell me what's the xy coordinate of this point. The rate, like we're starting at x equal 1, y equal 5, the rate describes how this point changes to become this point. The rate of change is 15 over 1. So that means the x value needs to change by 1, the y value needs to change by 15. So what's the new point? Show me hands. So what's the xy coordinate of this point? For Maya? So how many agree? 2, 20? 2 points, 3 for Maya. So this point is at 2, 20. That's what we mean by rate. Questions? Okay, the rate of change at a point to me can be confusing because I'm like, well, I can see the rate of change between 2 points because I know this coordinate, I know the rate, so I just go over, up, makes sense. Rate of change at a point seems kind of weird to me. Like, how is the rate of change at this point 10? Well, it was found to be 10, as Greta said, extra point for her, by making 2 really short secant slopes. We deduced that the rate of change must be 10. Well, what I like to do is I like to pretend, this is not mathematically correct, but it helps my understanding, that there aren't an infinite number of points, they're a finite number. If I zoom in enough, like I can somehow zoom in infinitely, this is what I would see. All the other points would disappear because I've zoomed in so far I can only see 3 points. I see the point at 1, 5. The very next point is 1 infinitesimal unit to the right and 10 infinitesimal units up. And that's why the slope or rate of change is 10. Okay? It's not reality. There's an infinite number of points. You can't do that. That is the idea. If you could zoom in enough, you would see this. Question. Cool. This example is showing a different place on the graph. Right here, the graph is steeper, so the rate of change is higher. If you come to this location, so moving the point, so I'm going to come down here to x equal 0.5. And now if I make the 2 secants infinitesimally short, or as short as the computer will allow, something like that, it appears that the slope at the point, the tangent slope, is going to be 5. And it is. So my imagination says, okay, I get it. If I'm looking at this point, I'm on a part of the curve that is not as steep. So if I move right 1 infinitesimal unit, I'm going to go up 5 infinitesimal units. Okay, that's the idea of a rate of change. Question? Okay. For this unit, what we need to do is figure out how to use the green cards, or the green rules, the green shortcuts, to find a new formula. This is the formula for finding all the xy coordinates. Using the shortcuts on the green card, you're going to learn that this is the formula for finding all the tangent slopes. On your calculator, this works great. Like Luke said, another point for him, just type that on your calculator, it'll tell you the slope. Don't get to use your calculator on the next test. You have to learn how to use the shortcuts instead. Using the shortcuts, you're going to discover this formula, 10x. This formula finds all the xy pairs. This formula finds all the tangent slopes. So if the x coordinate is 1, 10 times 1 is 10. The x-coordinate is 0.5. 10 times half is 5. That's why right here I'm representing that the rate of change at this point would be 10. The rate of change at this point would be 5. Question. Okay, next thing. As we learn the shortcuts, I'm going to be very picky on notation, because I've learned over 12 years that students who work really hard in the beginning to have the correct notation, slowly but surely, those students can use less and less notation and they have no problems. Like they do just great. Eventually they can use quite a bit less notation. Everything works fine. Students who try to shortcut the process from the beginning, it's a disaster. Okay? So if you don't use correct notation from the beginning, I will not help you. I just won't. Like if I look at your work and it does not look like my work, I will not answer your question, because you're taking too big of a shortcut and you're going to get a miserable test score, and it's going to take way too long to help you get caught up. So just from the beginning, you must use my notation. Like I'm really picky on this one because I've noticed over 12 years it makes a huge difference. With time, you'll just naturally start using less and less notation, and everything will be fine. Just don't do shortcuts at the beginning. Okay? Questions? So for this entire unit, the sheets I give you will be very small, because we're just practicing using the rules. So you don't do any work here. You do it on lined paper, either in your loose leaf binder or in your notebook is fine. I don't care which. But you must use the right notation. So here we go. So I'm doing 46 as an example. Just write down 46 in your notebook. And as always, you can't let yourself get lost in the computations. You have to keep track of the big idea. So we have on the board a formula. F of x equals this. Points for the whole room. What's the purpose of the formula? I'm tired of asking this, but you can't lose track of it. What is the purpose of that formula, Jared?
Gives points, coordinates.
Gives us x, y coordinates. We can plug in an x, we can find the y. You can also do it backwards. Plug in the y, find the x. How many knew it? Point, 2 for Jared. In the future, look, when I ask that question, if you can remember to say this, find all xy pairs, like how can I best remind you of this? It's like, I think we better say it the other way. Like when I ask, if you will say, oh, you plug in an x, you find a y. Or if they give you a y, you solve for the x. Like you say that, I will give you, instead of 1 point, I'll give you 3 points. Okay? Like you've got to keep that straight. Plug in an x, find a y, or they'll give you the y, you find the x. Both are going to happen. That's the purpose of the formula. Question? Awesome. Okay, our goal is to find a new formula whose purpose is to find all of the tangent slopes, which means we're finding all of the rates of change. So with this, we're just finding xy pairs, like the actual points. But with the derivative formula, we're going to find how fast the points are changing. We're finding the rate at each and every point. The way we do that is with the derivative operator. So the derivative operator looks like this. D over dx. Okay, derivative means slope. So the little d does not mean derivative. Don't ever say that. The little d means difference or change. Slope is how fast is x changing relative to y. It's change in y divided by change in x. So the d on the top means I want to find the change in the y coordinate. Well, f of x is a symbol that represents the y coordinate. So I'm going to write, I want to find the change in f. I want to divide that by the change in x. That's what derivative means. So derivative is the ratio. Derivative isn't the d. The D is difference. It's this picture again. We pretend we can zoom in so close that we can see from these 2 points the change in x is 1, but the change in y is 10. And that's why the rate or tangent slope is 10. This symbol represents exactly the same thing. Change in y divided by change in x. Questions? Okay, you'll see me write it this way sometimes. You'll see me write it this way sometimes. You need to be comfortable with both, because on the AP test they will use both notations. Those two mean the same thing. Questions? If you've had AP Physics and this feels like the same thing, that's really going to help you, but don't check out too quick. We have to go quite a bit farther than what you typically learn in AP Physics. So, it's algebra. If I use this operator on the left half of the equation, I must use the same operator on the right half. So I have to use the equal sign. On the AP test, if you do not properly use the equal sign, you lose points. So in this unit, I'm looking for the right notation, correct equal sign, no shortcuts. Okay? It's coming. So I apply the operator to the left, I have to apply the operator to the right. Like that. Questions? Cool. F of x means the y coordinate. But this formula also means the y coordinate. That's why these two halves of the equation are equal. That should make sense to you. What I just said didn't make sense. Wave so we can talk about it some more. This says f is just another symbol for this equation. So if I take the derivative of f, it's the same as taking the derivative of the equation. Questions? Cool. Watching for twitches. Good. Scratching's all right. Okay. Just a different way of writing it. So again, you'll see this as well. I'm not going to write it both ways every time. It's just this first time to make sure we're noticing the two different kind of styles of notation. Okay. Questions? Awesome. Another notation here you've already seen. I've shown you this one. This can also be written like this. F prime means the same thing. So. Okay, now we're here. If you type this on a calculator, this will give you the tangent slope. Okay, the calculator knows how to deal with that. The computer knows what to do. By hand, it's not helpful. Like from this, we can't really find the tangent slope easily. It would be a bit of a challenge to create the two secant slopes and then figure out how the secant slopes get shorter and shorter. Would not be easy with this formula. So we're going to use the green shortcuts to change the formula. And we just have to use the rules as they are outlined. So the way the rule card works, and you'll get this memorized fairly quickly as you do the homework. The way the rule card works is you look down the card. You're looking on the left side of the card at each and every box. You're looking for a formula whose format matches this. If you want it to look like this. As I look down the card, hold on a second, let's make this a little bigger. Here's the full card. So what I notice is, I look at the easy ones first. I do not have a derivative of an exponential function. E is not involved at all, so I'd skip that rule. ln isn't involved, nor is square root, or this is like a number to a power, tangent, sine, cosine, inverse. None of those fit at all. I just skip right past them. I come further down the page. Okay, the chain rule. Everyone look. Okay. We won't use the chain rule by itself for a while, but the rules I've given you already incorporate the chain rule. Like I've helped you make a quick shortcut that most textbooks do not. Most books do not start with this version of the power rule. You start with a simpler version, but I found that that's actually harder. It's easier to start with this version of the power rule, which already uses the chain rule with it. So this is a combination of the book's power rule and the chain rule. So don't worry about the chain rule for now. You're already using it without really realizing it. So anyway, so skip the chain rule. Not working with a quotient, two things being divided, so I skip that. We'll learn about this later, what a derivative of an integral is. It's not inverse. My voice is failing rapidly. It's this one right up here. We're dealing with a power function. So back to here while I get a drink of water. The reason I know it's a match is right here. I've got d over dx of a function right here that is being raised to the second power. That matches this rule perfectly. This says d over dx of some function being raised to some power. Unless it's a perfect match, you can't use the rule. So if it's not a perfect match, you're off track. You're using the wrong rule. For our class, there's always a rule that works. You may have to do something algebraic to make your expression look like it fits the rule, but there's always a rule that works. You're never going to run into something where the answer is, oh, we can't do it in our class. So anybody having trouble seeing that the rule I want to use is the power rule? Okay, equal means these two things are the same. So equal is telling you, hey, you have this expression, or think of it like this. Instead of writing what you see in blue, you can write this instead. You simply have to identify what is the correct value for n, and what is the correct value for g of x. Okay, the g of x is just generic for some function. So raise your hand. Who can tell me what the power of n is? What's the value of n, and what's the g of x in this problem? Don't overthink it. It's not hard. What's the g of x and what's the n? Water. Brecken.
N is 2 and g of x is 3x, then the fourth minus 5.
How many knew it? 2.3 for Brecken. So the rule says this is equal to n, which is 2. So I write down 2. Parenthesis g of x close parenthesis and subtract 1. And then, because I have already combined the textbook power rule with the chain rule, my rules always end with this extra operator. Like when you are finding a derivative, you always end with finding another derivative. It's how the rules work. These rules are really just found by doing secant slopes. But the math that's in between is a little bit hard. And you don't get tested on it, so I don't really want to spend time on it in class. But anyway, my end of the rule has to use this. So I write d over dx of the g of x formula, or g of x function. So when you're finding a derivative, you apply a rule, you will often end up needing to find another derivative. Everyone tends to think of it like that movie Inception, where you started with one derivative, you've now gone one layer in, you've got to find another derivative. You're working your way from the outside of the function inward. Okay, layer by layer, please say.
So when you have f of x, can you always make it d over dx?
Keep talking, not sure what you mean.
Like, when you're given that equation, how did you know to put, like, d over?
Oh, really good question. I just didn't, my bad, I didn't understand. 2 points. I think this is what you're saying. Given any formula, just call it whatever you want, call it h if I want. Something like that. Hands up for the whole room. What's the purpose of this formula? Let's go, Brenda.
Find y values for they're going to give you x. Or they're going to give you y and you find x values.
There you go. So you plug in a y, plug in an x, find the y, that gets too many things. So you can plug in x, find y, or given y, I can find x. How many knew it? 3 points, 4 for Brenda. Sage's question, well, that's just going to give me all the points, all the values. What if I want to know how fast those values are changing? I want to know the rate at which one point changes to another. Just like this. I want to know the rate at which one point becomes another. How fast that happens. I want to know the tangent slope. The derivative operator is a mathematical way of doing that. So I take the derivative operator and I apply it to both sides. Like this. That's legal because it's just algebra. I'm applying an operator to both sides of the equation, therefore the equation is still equal. But this side now represents something different. It represents a formula whose value, whose y-coordinate, will be the rate or tangent slope of this formula. That's what we talked about in Unit 1. I don't know if that was your question, though.
No, that is.
Okay.
So my question is the same as Sage, but just to clarify, every time that we get a problem, we're going to be using the d over d of x. So that's like the first step that we can always put back.
As long as the question is asking you to find the derivative.
So if it's giving us the y value, then we're going to be doing something different.
So what's going to happen is, if they give you a formula, you're thinking, okay, I can use this to find all the x's and y's. But if for some reason I need to use this to find the rate at which the x's and y's are changing, then I'm going to want to do a derivative. So I'm going to do this operation to both sides of the equation. That will always be the first step. And then we dive into the rule sheet to figure out how to decode it, basically. Is that your question? 2 points for Cassidy. Please.
So are you changing the function from f to f prime and then do it again f double prime?
Perfect. Perfect. So in Unit 1, we talked about how f relates to f prime relates to f double prime. But we didn't like really create them. We just kind of used stuff they gave us. This unit, we are creating them. We have a formula for h, and we could graph that. We're going to create, using the rule sheet, a formula for h prime. It's perfect. 2 for Kate. Anybody else? Okay, the bell ring in 20 minutes. No homework tonight, so good work. Good work.